Good afternoon, ladies and gentlemen. I hope you had a pleasant lunch and you have renewed forces for this afternoon session, which will center around secondary raw materials, waste processing and recycling schemes. And I would like to give the floor to my colleague Susanna Shara, project advisor at HADEA, who will be chairing this afternoon session. Susanna, up to you.
Yes, I was indeed. Can you hear me well now? Thank you. Thank you very much, Yolanda, and good afternoon to everybody. This session of the afternoon focuses on secondary raw materials, improving resource efficiency and circularity. We will attend 6 presentations of Horizon 2020 success stories addressing different aspects of the subject, such as the recovery of rare earth elements, platinum group metals, sulfidic mining waste, waste streams from primary aluminium production, as well as identifying good practices for municipal waste collection and voluntary certification scheme for waste facilities. Regarding the structure of the session, the first 4 success stories will be presented before the coffee break, and the last 2 after the break of 30 minutes. For each project, 15 minutes have been allocated, including the time for questions using Slido. Therefore, I invite the attendees to use Slido at any time during the presentation. Questions will be read and answered after each presentation. The first success story of this afternoon is the project Secrets, that deals with recovery of rare earth elements from a side stream in fertilizer production for their application in electric vehicles, industrial motors, and wind turbines. To present this project, we have with us Pauline Schrobot. Pauline is a sustainability consultant at Quantis since 2017. She holds a Master in Environmental Science and Engineering from Swiss Federal Institute of Technology in Lausanne, with a specialization in soils, water, and ecosystems.
Susanna, sorry to jump in. There is some logistic complication with Pauline. I suggest, if possible, that we start with the presentation of Platinus, as
Yes.
to give time to solve this issue.
Pauline just joined.
Okay. Then it's all good. Sorry.
Thank you, Yolanda. At Quantis, Pauline is involved in agricultural modeling projects and database development. The floor is yours, Pauline. Are you ready?
Hi, everyone. Yes, I'm ready. Thank you. So you are sharing the slides, right? Okay. Hi, everyone. So my name is Pauline Crobot. I'm working at Quantis, like I was just introduced. Quantis, just in a few words, we are helping our clients on their sustainability journey, and we base our assessments on a science which is called life cycle assessments. And this is where we work with a lot of different industries, and we're also involved in European projects, and that's what I'm here to tell you about today. So next slide is just introducing quickly this European project I was mentioning, which is called Secrets. Secrets stands for Secure European Rare Earth Elements. It started in 2018, and it's going to finish next year. We are 8 partners on this project. So we have Yara on the top. You see Yara, Retec, LCM, and Vacuum Schmelze, who are part of they are the technical partners. They are piloting the project. Then you have Ineris and Quantis. We're responsible for the sustainability and risk assessment. Prospect Institute is doing the public engagement, dissemination, exploration, and Sintef is managing the whole project, basically. So next slide. So as you all know, permanent magnets are nowadays used in a lot of different technologies, especially green technologies, and certain permanent magnets are produced in Europe. However, the whole upstream of that supply chain, the global production, the mining, the refining, the rare earth oxide separation, etc., is dominated by the Chinese market. So the goal of this project is, of our project, is to really look at the possibility of making European rare earth elements and producing basically European permanent magnets. And that's what we are piloting at the moment with the different partners on the project. So next slide, you can see a first, just very quick overview. I'll just go into details later of the supply chain we are studying. But it's just to illustrate the fact that we are really working with our partners so they're working on their pilot and they're giving us the data, and we are really building this data foundation with them to be able to really assess the life cycle, the environmental performance of this new technology. Just a quick word, if you don't know life cycle assessment, this is really a science taking into account every step of the life of a product, from the raw material extraction in that case, until the use and the disposal. But in our case, we look at the permanent magnet, so it's until the production of a permanent magnet in Europe. Next slide. Okay, so just again, a quick overview of how we are working. This is general for life cycle assessment, but it is also what we are doing right now with Secret. So we have several systems under study. We do the data collection. Then we have a life cycle inventory to be able then to model the different systems that we're looking at in a software and run the results. So if you go to the next slide, you just have the two systems that we are comparing at the moment. So we have the Secret system, with our production of 1 kilogram of permanent magnet from a European innovative supply chain. So we're looking at one main production pathway, and we have several assumptions that we also, of course, detail in our analysis. One of them being, for instance, that to produce this 1 kilogram of permanent magnet, we just assume for now that all the rare earth elements are coming from our European system. And we're comparing this with the baseline. So again, we look at the same functional unit, which in our case is the production of 1 kilogram of permanent magnet. And in the baseline system case, the production pathway will be from what is currently happening, so mainly from China, and from two different sources. So from mining bastnäsite and monazite ore for neodymium and praseodymium, and from iron adsorption clays for dysprosium. Now, if we look a bit closer at the different supply chain, just for you to understand what do we take into account or not. So for the Secret system, basically what is innovative in our system is that the source of the rare earth is coming from Yara, which is a fertilizer producer. And so they have an already functioning facilities, etc. And out of their process, we can extract some rare earth elements. And that's what Retec is doing. So we have this already existing fertilizer production. We just extract the rare earth elements, which is not influencing in any case the quality or the amount of production from Yara's perspective. So it's just like something which won't be used otherwise. So Retec is extracting the rare earth and separating the oxides. And they're sending them to LCM, where the metal and the alloy production is taking place, which is then sending the product to vacuum schmelze, actually producing the magnets. And you can see in red, this is again the functional unit I was mentioning before. So we have this 1 kilogram of permanent magnet. So this is the Secret system. That's everything that we take into account in our system boundaries. And I have the same slide for the baseline, where you can see that again, we look at so what we call in LCA cradle to gate. So we take into account the rare earth oxide production and separation, both for NdPr and dysprosium. Then we have the metal refining. We take into account the same steps in both systems, and same for the magnet production. So the real difference here is everything which happens before the metal refining. In terms of technology, then of course in the modeling there are also differences between a production happening in Europe or in China. For instance, for the electricity mix, that's the obvious example. And again, we look at just 1 kilogram of magnet. That's the functional unit. Sorry, yeah, you can go to the next one. Okay, so for the secret system, we had access to primary data, obviously, because we were closely with our partners and they were able to give us some data that they had available. So first, everything that I'm talking about and I will show right now are more the preliminary results, because it's a long project. They had to do pilot plans before they could they're actually planning to scale them up. So yeah, we're working with them to get their primary data. And for the baseline, we didn't have access to primary data in China, but we were able to browse a literature where there is a lot of different sources and articles there, and kind of take the best out of it to model the baseline. So that's the two sources we used for getting the LCI, the life cycle inventories. And then we modeled the results in our software, CIMAPRO, and ran the results to really have a look at the results. So I can show you the results right now in the next slide. I think it's just, again, a disclaimer that, yeah, it was preliminary results that we're going to be refining. Yeah, exactly. So so these are just the first preliminary results that we got. So you see on the y-axis, so we are talking about percentages right now, because we have different impact categories. So we're looking at what is the worst case versus the other one. So if we look at climate change, for instance, you see in red the baseline system or the baseline supply chain, which has obviously a much greater impact than the secret one. And it's the same for the other indicators. So these results are again for producing 1 kilogram of permanent magnet, taking into account everything from cradle to gate. And you see, for instance, for the climate change so these are not the exact numbers, it's kind of an order of magnitude, but for the baseline, we are around 1 kilogram of CO2 emissions, CO2 equivalent for producing 1 kilogram of permanent magnet. And for the secret supply chain, we are so far, again, because we are refining the results for both supply chains, around 20 kilogram of CO2 equivalent. The main contributors, so that's the next slide, the main contributors for the baseline are the first step, which is the rare earth oxide extraction and separation. So that's really the main contributor. I think it's from, around 60% or something of the impact, followed by the permanent magnet production step. And that's where it becomes interesting, because in the secret supply chain, the main contributor is the permanent magnet production step. So we see in the secret system that the fact that we are getting rare earth elements from an already existing fertilizer production is reducing dramatically or drastically the results, actually. And this is due to several factors. First, that, of course, in the processes, the current processes happening in China are quite intense in terms of energy and in terms of impact on the environment in general. And also that for the fertilizer process, of course, we allocate a part of the fertilizer production to our system, but even by doing that, we see that the secret system is showing lower results in terms of environmental impacts. Okay, so that was the main just results, in a nutshell, basically. We're going to go also into more detail for the different contributions and for the different indicators in our assessment and in the second round of data collection. which is happening right now. Yes, so the conclusion, I think it's the last slide. So, oh yeah, I didn't mention, we're also doing the life cycle costing, which I didn't show because we don't have the results yet either. But basically, it's doing the same as for life cycle assessment, but with costs instead of material flow. So we can see where are the hotspots in terms of costs. We are also refining the results right now. And just I wanted to say a quick word about the data quality. So one of the main challenges that we encounter in LC in general, but especially in that project as well, is the fact that, so for the secret system, we had access to very good and robust data from our partners because we have good interactions with them. But for the current practices, mainly happening in China, of course, there are a lot of literature, but we see quite a challenge in terms of data quality, data transparency, and consistency in general. So it's not an easy exercise to kind of compile all the different sources and find out what the best data out there. Probably because the best data are not existing yet. So we were in contact with other partners from other European projects to kind of try to find out get the best out of the data available so far. But this is really a challenge for us at the moment. So yes, I think that's it. Almost on time.
Perfectly on time, Pauline. Thank you very much for this very, very interesting presentation, and congratulations to you and to all the other members of the consortium. We have one question on Slido that I'm going to read for Sure. Pauline. Thank you for the impressive presentation. Great and interesting results. Are the LCA and LCC available for open consultation?
I think no, so far they're not. The deliverables are confidential. I mean, the sources I've been using for the baseline are out there, and they're open source, of course, so everyone can have access to them. For the secret system, no, it's not. They're not available.
Okay, thank you very much again, Pauline. It's now time to move to our second success story of this afternoon, and it is Platinus. Platinus is about platinum group metals recovery from spent autocatalyst WEEE and anodic slime. For the presentation of Platinus, we will have three speakers: Laura Sanchez Copido, Giovanna Nicole, and Esther Lizasoain. Laura is since 2005 a senior researcher at Tecnalia in the Department of Materials and Processes for Energy and Environment. Her work has been focused on the study of deep euthetic solvents and ionic solvent liquids as new solvents, fluids and electrolytes for diverse applications, with a special focus on the valorization of metals and high-value products from primary and secondary raw materials, including spent magnets, catalysts, batteries, plastics, or mining streams, amongst others. Giovanna is a specialist in material science at the Centro Research Fiat, where she works since 1994, dealing with subjects such as metallurgy, metal casting, and catalysts for emissions after treatment systems. She has been involved in several research activities, from lab-scale characterization of material to modeling. Esther is since July 2020 a researcher at Tecnalia in the May I continue? Esther is since July 2020 a researcher at Tecnalia in the Energy and the Environment Division. She is specialized in life cycle assessment, having carried out studies on the use of slag on roads, analysis of traffic emissions, durability of asphalt pavements, and analysis of additives to improve asphalt mixes. Currently, her research is focused on the analysis of chemical processes for the recovery of critical metals. Ladies, the floor is yours to present Platinus.
Okay, thank you very much, Susana, for the nice introduction. Please, today I will present the Platinus project. And as Susana said, Giovanna and Nicole from Research Center of Fiat and Sterilization will be with me giving this talk. So you can show the slides, please. Okay, next, please. So first of all, I would like to give you an introduction of the motivation of the Platinus Consortium to do this project. No? As you know, the platinum group metals are critical raw materials, are considered critical raw materials by the European Union, and this is due to different factors. One of them is the economical importance of the PGMs, as they are used in very important sectors such as automotive and electronics. Another important reason is also that Europe is one of the biggest consumers of PGMs in the world, and a big important reason is the risk of supply that we are facing with these PGMs. This is in part due to the scarcity of these materials in the earth, or these elements are in the earth, but and also due to that these elements are, the mining is done in geopolitically unstable areas. We have to add to this that the process that currently produce the PGMs have also a high environmental impact. And it is true that we have currently there are PGM recycling processes, but these also have some challenges such as high energy consumption and the fact that they are quite centralized because of the high capital investment cost, no, for these recycling processes. So this is one of the reasons, for example, why the currently available recycling processes don't fill the gap between the supply and the demand. No? So, motivated by these reasons, the Platinus Consortium proposed the Platinus, in which the general objectives have been the development of a novel cost-efficient PGM recovery technology based on ionometallurgy, solometallurgy, and hydrometallurgy. Another objective has been one of the objectives has been to reduce energy and to miniaturize the currently recycling processes. Of course, to reduce the environmental impact of current processes when possible, and to do these developments in an industrially relevant scale. In particular, in this project, we have targeted TRL 5. Next, please. So in this slide, we can see the Platinus value chain, the partners, and the roles. The project has been divided in 10 work packages. The first one has been devoted to the management, and the rest, in the case of work package 2, this has been devoted to the pre-processing and supply of the different PGM containing waste, autocatalysts, mining wastes, and electric and electronic waste. The partners leading this work package have been Ford, Monolitos, Boliden, and CRF. Then in the next work packages, in the next 3 work packages, the advanced PGM recovery technologies have been investigated and developed by 5 R&D centers: Vito, Sintef, Vienna University of Technology, Tecnalia, and KU Leuven University. And once these technologies have been investigated, the best performing technologies were selected and validated in work package 6, in which the leading partners were Monolitos, Johnson & Matthey, Porotosan, and CRF, together with the partners who developed the selected technologies. And then we have also other non-technical activities such as life cycle assessment and life cycle costing, and exploitation, which was led by Aqua and Tecnalia. Also exploitation, dissemination, and communication activities, which were led by P&O, and clustering with our relevant projects, which has been led by Tecnalia. Next slide, please. So in this slide, we can see more details about the PGM recovery technologies that have been investigated. All the technologies have been classified like in 3 blocks, so that correspond each of them to one work package, which correspond to the main stages in PGM recovery processes, or almost in many processes, no, hydrometallurgical processes. So in the case of the leaching block, let's say we had microwave-assisted leaching and also leaching using non-conventional solvents such as task-specific ionic liquids, deep protective solvents, and non-aqueous solvents in the solvometallurgy. With respect to the separation work package, in this case, we studied selective absorbent materials, hybrid absorption materials as solid liquid separation technology, and non-conventional liquids in situ reduction and supercritical CO2 as liquid-liquid separation technologies. And finally, in the recovery work package, we have studied electrochemical and gas diffusion electrocrystallization as advanced technologies, but this has been also combined with other more conventional techniques such as simple washing or traditional recovery steps. And all these techniques have led to final products which have been PGM metals or oxides or PGM salts, depending on the particular use we were considering. I will explain more in detail later on. Next, please. So based on different criteria, after the research phase finished and doing the assessment considering different criteria such as high efficiency, reduced cost, reduced environmental impact, and so on, one technology was selected for each of those stages I mentioned before, and were selected for the final Platinus process. No? In the case of the leaching, microwave-assisted leaching was selected due especially to the very high PGM leachability and also the fact that it was using milder leachants and the state-of-the-art leaching processes for PGMs. In the case of separation, ionic liquid-based liquid-liquid extraction was selected as this technology was capable of separating the PGMs coming from the previous step in the Platinus process, and also thanks to the high selectivity to separate PGMs and the fact that the extractant could be recycled. And finally, in the recovery part, we selected the gas diffusion electrocrystallization as it was compatible with the previous stage. I mean, it was able to recover the PGMs from both the leaching or the separation solutions. It depends on the case. And it was very interesting also that it was electrolytic process and it didn't need any chemicals. No? So that was very attractive, and that was the reason why it was selected. So these technologies that have been selected, the feasibility has been demonstrated for different types of waste materials, namely autocatalyst, electronic waste, and tailings. All of them, the feasibility has been demonstrated, obtaining different types of end products. Right? Next, please. So in this slide, you can see, in the previous slide, I was talking about the development activities, but as I said, then with the selected technologies, we did a validation. So the validation has consisted in applying those technologies, starting from end-of-life autocatalysts that were pre-processed with the technologies that we consider in the project in Work Package 2, and they were subjected to the microwave leaching, the liquid-liquid separation with ionic liquids, and the recovery techniques, and with the objective of that final product that we are achieving with these technologies, producing new autocatalysts. I mean, the new autocatalysts have been produced, and then the industrial partners have validated using their standard test. They have validated the performance of those catalysts produced with the PGM recovered in Platinus. And now, I'm not sure if Giovanna is already there. I have seen some messages. I would like to give the floor to her. Is she available?
Yes.
Can you hear me?
Can you hear me? Okay, perfect. Thank you. I hope you can see also, because I see me on the screen. Okay, perfect. Okay, so next slide, please. Okay, so yes, as Laura said, the validation tests were performed in the first phase, the lab scale level at CRF, used on a synthetic gas bench where a mixture of gases is mimicking the real working condition is applied. Here in the slides, you can see the measured key parameters for the three-way catalyst. The graph on the top represents the conversion efficiency of the main pollutant, so the carbon monoxide and the hydrocarbon on the graph 1, and nitrous oxide on the graph 2. If you look at the broken and solid line, you can see that the curves rapidly increase so the conversion is rapid and is effective for all these materials, and mainly for the Platinus flowsheet PGM. On the graph 3, you can see the light of temperatures, that is the temperature corresponding to the 50% of the conversion of the pollutant. So you have here the carbon monoxide, hydrocarbons, and nitrogen dioxide, and the most efficient catalyst is the one that has the lowest light of temperature. On the graph, on the chart, on the in chart 4, you can see another important parameter, that is the oxygen storage capacity, that is the ability of the catalyst to store and release oxygen for the oxidation reactions. And the most efficient catalyst is the one with the highest oxygen storage capacity. And so also in this case, you can see that the Platinus flowsheet PGMs recycled as the best performances. Next slide, please. Okay, here you have the same key parameters for the diesel oxidation catalyst. Also in this case, you have the conversion efficiency in graph 1 for the carbon monoxide and the hydrocarbons. And in the graph 2, you have another important key parameters, that is the nitrogen dioxide formation. That is important because it's the ability of the DOC to produce the NO2 that could be available for the devices downstream to the an after treatment system. On the graph, on the chart number 3 and the chart number 4, you have the light of temperature for the carbon monoxide on the graph 3, and for the hydrocarbons on the graph 4. Here also we can see that the most efficient catalyst is the one that has the lowest light of temperature. That is in this case also is the Platinus flowsheet PGM recycled. That is that shows so quite good, very good performances. Next slide, please. Okay, then the performance of the two catalysts compared with the Platinus and benchmark recycled PGMs were also analyzed in a comparative methodology by the other partner for Otosan at the full scale level via accelerated dyno test. As I said before, one of the main functions of the DOC is the oxidation of a nitric oxide to the nitrogen dioxide. So the NO oxidation efficiency were analyzed comparing the NO and NO2 at the inlet and the outlet of the catalyst. And the DOC produced with the Platinus synthetic PGMs material oxidize NO and NO2 more efficiently than the DOC produced with benchmark PGM, as you can see in the graph below. Next slide, please. Okay, another important function of the DOC is the oxidation of the unburned hydrocarbons, which is an exothermic reaction. So is the generating an increase of the temperature available for the downstream devices. So it's an exothermic reaction that increases the temperature of the exhaust gases. This in temperature increase increase is essential for the regeneration of the diesel particulate filter that usually is placed downstream to an after-treatment system. So in the graph on the left side of the screen, you can see the results for the fresh state catalyst, and on the right side, the aged state catalyst. You can see that at the fresh state, the Platinus synthetic PGM yielded a very high hydrocarbon oxidation efficiency. Then it is able also to reach a very high temperature that is 500 degrees, that is the desired temperature. At the aged state, the two catalysts show quite similar oxidation efficiency, and the temperature profile are also very similar. Okay, this concluded the validation test. I think that Esther will be next.
Yes, thank you, Joanna. Next slide, please. Okay. Life cycle assessment was performed to determine the environmental impact of Platinus flow sheet, to identify which are the key contributing parameters, and therefore to support its optimization. And the ELCA was performed considering 1 kilograms of PMs recovered and the 8 impact categories that can be seen here in this slide. Results show that the liquid-liquid separation, that is the process shown in yellow, is the process that is producing most of the impact, reaching the maximum in the photochemical oxidant creation potential and the minimum in the eutrophisation potential. And on the contrary, GDX, that is the one in orange, is the technology that is producing the lowest impact. Its contribution being lower than 2% in all the categories, except in the eutrophisation potential impact. However, we should take into account that not all the technologies try to recycle the chemicals, and besides, the upscaling of the energy consumption was made in a linear way, so these results can change as the TRL of the technology increases. Next slide, please. The economic analysis was performed in a very similar way, but in this case, a fictitious plant was considered, and the maximum capacity of this plant was 100,000 kilograms of autocatalyst treated per year during a period of 15 years. My screen was better, but all the investment made by microwave leaching was like the biggest, followed by liquid-liquid separation, and is this later technology the one that presents the higher operational costs. Regarding the revenue that can be seen in the right diagram, it was supposed that the recovery yield of the first year of operation of the plant was the same that the recovery yield achieved in Platinus, but an improvement curve was supposed until industrial yields are achieved at the end of the operation of the plant. And well, this improvement course obviously affects the revenue and the results. Next slide, please. So when we consider all of this, the incomes and the expenditure, we can see that the investment made can be recovered in around 6 years. That typically investors are looking for less than 5 years payback period, but they accept between 5 and 10 for new medium-scale developments. So 6 years will be totally acceptable. And besides, in the right diagram, we see the comparison of the production cost of Platinus with several references related with the state of the art, and we see that Platinus is likely more expensive than the reference for the 2 first years of operation of the plant, but it becomes
So we don't have questions on Slido, and now we are moving to the third success story of this afternoon, the project Nemo. that addresses the recycling of low-grade sulfidic mining waste for producing critical metal, mineral, and construction raw materials. For its presentation, we have two speakers, Arne Pease and Thomas Lapau. Arne Pease is since 2019 working at Vito to transform a wide variety of residues in cement and concrete constituents. He manages the research in a few projects and tries to understand and communicate about how industrial residues can be used in construction materials. Thomas is a CTO at Resourceful since 2018, where he's developing ecological friendly building materials and enthusiastically committed himself to a more sustainable and circular construction world. So the floor is yours. Please try to keep the time allocated to your presentation.
Yes, hello, good afternoon, everyone. This is Arne Pease from Vito speaking. I'll just wait a bit. Yes, this is my title slide. So I'm here to talk about the Nemo project. You see the title in full on this slide. It's about near zero waste recycling of low-grade sulfuric mining wastes for critical metal, mineral, and construction raw material production. And we will highlight the case study in this project about the Tara mines. Next slide, please, where I will show why we do the Nemo project. So the Nemo project is about the valorization of extractive waste, also known as mining waste or tailings. And you can see here that there is a lot of mining waste available. There's also a large historic stockpile, and these wastes can cause environmental problems such as mine drainage or even catastrophic events like tailing dams breakages. And in response to these problems and the call to arms of the EIP raw materials, we launched the Nemo project to have this as a resource recovery opportunity. And now I will present the next slide. So here you can see the Nemo concept as a whole. So we tried to use the sulfidic mining waste and recover first some valuable metals, and also to extract some hazardous components from the tailings. And then as a final step, when the valuable metals are out, when there is no hazardous components anymore, we try to use the clean mineral fraction in cement, in concrete, or in construction materials in general. So in the next slide, I will present a bit about the Nemo Consortium. So we are not doing this alone as Vito and Resourceful. It's a whole European consortium spread across Europe, coordinated by VTT and situated for a large part in Finland and Belgium. And the next slide, I will explain a bit more about the project and its structure. So there are 3 case studies in the project. So the 3 studies of mines of 3 different types of tailings. So there are mines in Finland, and there's a Tara mine in Ireland that we are investigating. In the next slide, there's the different work packages of the project. So there's first the bioleaching part. So there you try to leach the tailings and extract some metals from it, or to decompose the sulfide minerals that are in the tailings. And then in work package 3, there is the metal and mineral recovery from this leached product. The residue from the leaching we try to apply in the minerals and upcycle them in construction materials. And then on the next slide, you see like this horizontal work packages which work on the sustainability analysis, on clustering with other projects and management and these things. So the next slide talks about the replication for different case studies. So in the project, we try to focus on the 3 different case studies I mentioned before, but already in the project, we try to target some different mines and get some other materials to see if the technologies we develop in the Nemo project, if they can also be used on other mine tailings. So this is a very important step for Europe to do this replication as well. So then in the next slide, I will go a bit more in about the case study of the Tara mines. So this is the case study we will highlight in this presentation, and where Thomas will talk about later. So in this case study, we got the mine tailings from Ireland, and we used them for the clean mineral residue upcycling. So then in the next slide, we will start doing the transition. So you can see here already the map of the town near Tara, and then Thomas will take over and talk about this study.
Yeah, thank you very much, Arne, for the Nemo introduction. So this is, let's say, the place where we got the tailings from for our, let's say, specific work package in the Nemo project. And we focus basically on the very fine fraction. So part of the tailings comes back into the mine, the coarse fraction, which is used as backfill, but there's still an enormous amount of material which is let's say dumped in a pond, and that this fine fraction or tailing slimes, that's actually the ones we're focusing on. In the next slide, please. There you see a live image. This is how the starting material looks like. So one of the goals of this Nemo project is not, let's say, do it at lab scale, but really go the full size towards TRL 8, TRL 9. So we need a lot of material, and here is where the, let's say, the team from Boliden dig out in total more than 20 tons of dry tailings. So in the beginning they're wet, and that's actually where the project starts from. Next slide, please. So what we try to do with these slimes, you see that they're, let's say, very fine and very sticky material. So one of the first ideas is to combine these fines and granulate them into kind of artificial aggregates. And the second route that we follow is to calcine this material to see maybe there's still any reactivity in it, or and try to use that as a kind of cementitious material. And the last one is actually these two materials, combine them and make some concrete demonstrator cases. Yeah, next slide. So the overall idea of the agglomeration is actually trying to take these fine materials and stack them together with, let's say, as minimal cement as possible, and like this recover the material. Normally, you know, the view you have is actually the final product you have after the granulation method. So this material comes out very nice spherical shaped material, quite lightweight, which can be used in a concrete application. The next slide, please. Yeah, here we see the case where we calcine this material. So if there's any reactivity, by giving it a heat treatment, we can, let's say, make the tailings maybe react as a cementitious material, or which is for the Tara case relevant, destroy, let's say, annoying certain phases which could harm the reactivity or the concrete material. These are some views on the flash calciners available at our partner in ThyssenKrupp. As you can see, we went actually through all TRL levels from a very small scale up to the TRL 8, where we flash calcined the final material. And that's what you see in the next slide. Where we're, let's say, as a work package 4, I think we're quite a team, and we collaborate nicely together. So this is where we flash calcine together with the team at ThyssenKrupp. And the main goal here was to avoid or let's say remove the pyrite content. So the tailings contains still a fraction of pyrite, which is unwanted as it can expand. And by giving it a flash calcination step at 550 degrees, we convert the pyrite then partially in hematite and a small fraction of anhydrite, which are not, let's say, considered harmful in cement. So then when we have these materials, if you go to the next slide, what we want to do is basically make concrete, maybe, let's say, we try to make it as low carbon concrete as possible. So if you consider traditional concrete where you have cement as the glue, the binder, which you mix together with water and then sand and coarser stones, we try to, let's say, look at all the different raw materials used for concrete, especially look at cement, as this is, let's say, having the largest ecological impact, which we try to replace with tailings and slags and ashes, so secondary materials, and use this as a binder for the sandstones and also the artificial aggregates. Just adding water is not always enough. Sometimes you need this, what they call activators or special additives to make these, let's say, secondary raw materials reacting towards this low carbon concrete. Yeah, and next slide, there you see let's say the 3 types of concrete we demonstrate in this project. So the first one is a pressed paver, and then the middle one is ready mix concrete that are the concrete trucks driving around. This is done at the partner in Nemo, Jacobs Beton, Jacobs Concrete, and in the end an example of a prefab sandwich panel produced with self-compacting concrete. We go quickly, let's say, through the 3 cases. The pressed paver is actually the pilot which is already done, which you see in the next slide. Here we made 800 of these units, really TRL9 in an industrial facility at, let's say, industrial speed also, where we produced these complete blocks and also test them according to the European standards, where we have, let's say, quite nice results in terms of strength and water absorption. We let's say, definitely fulfill our required properties, and we are further investigating the durability of these pavers. In the next slide, you see in the next slide, you see our preparation for the ready mix concrete. That's really, let's say, a big market. I think 50% of all the concrete is casted from a truck. And there we try to minimize the amount of cement by using partially slags and the Nemo tailings. And we managed to go from, let's say, 140 kilo pure Portland clinker towards 80 kilo Portland clinker in our last Nemo reference. Apart from just making things hard, let's say that's the easiest, it should also be a nice workability and have long durability classes. So that's what we're at the moment investigating. And on the right side, you see, let's say, 3 demo slabs we casted with this with the Nemo material. Then in the last demonstrator, we try to make self-compacting concrete. It's a pity the movie is not fully playing, but there you can see it's actually concrete that levels itself. You don't have to work on it. It's easy to make, but let's say it's easy to work with, but it's more tricky to make as the flow is extremely critical. So that would be our 3rd pilot case, where we use the tailings partially as a filler, so a limestone filler replacement, and a second one will be as partially as a binder. So let's say that are in brief our 3 concrete demo cases. I think the next slide you will find all the info and let's say all the updates on our pilots on the website of Nemo. And if you have any questions, I think in the last slide you see our contacts of the project coordinator and all the people involved. Thank you.
Thank you very much, Arne and Thomas. We don't have by now questions on the slide, so we will move to the 4th and last success story before the break. It is for the project removal. It deals with the recovery and valorization of waste streams from the primary aluminium production, and will be presented by Efthymios Balomeonos, a senior consultant at Mytilineos. Since 2008, Efthymios has been working in the Laboratory of Metallurgy as a postdoc researcher focusing on sustainable process development, CO2 mitigation strategies, exergy analysis, and resource utilization efficiency. Efthymios, the floor is yours.
Thank you very much. Welcome everyone to our last case for today. I have a lot of slides in my presentation. Most of them are information I think people can view afterwards because we have a limited amount of time. So let's move straight to it. Removal is a project that has started 3 years ago. And it's dealing about reusing the bauxite residue coming from bauxite residue. Next slide. Bauxite residue is the main byproduct from the alumina production. And currently there's only 3% reuse of it worldwide. In Europe, it's even less. So next slide, please. Next slide and next slide. The project is, next slide, is focused on several pilot activities. Next slide, please. Yep. Yeah, several pilot activities with 4 main objectives in mind: to use as many waste as possible, to recover critical metals, to develop marketable products, and to customize the solution, which will be a sort of mix of the various pilot cases for each alumina plant in the project. So our goal is near zero waste and near break-even flow sheets. Next slide. And with this information, yeah, you can see here some of our pilot location. Next slide. We don't need to spend time in this. So our first pilot is dealkalinization, removing the soda from bauxite residue. Next slide. And you can see here we have 2 pilots: a small scale pilot that took place at Mytilineos and just processed around 600 kilograms of bauxite residue, removing soda and creating a new byproduct that's now rich in calcium and does not have the alkalinity that was a big problem of the bauxite residue. Next slide. The soda can be recovered and reused in the alumina production process. And here you see the larger scale pilot that is currently working at O'Guinness refinery in Ireland, the same technology, and it has already processed 3 to 4 tons of bauxite residue and will keep on working until the end of this year. Next slide. So another use, the first one, let's say, was to recover soda and remove alkalinity, which is a problem with this byproduct. The second use was to use it directly as a green sub-base for roads. So next slide. Here the technology is kind of can be summed up in this simple equation. You take bauxite residue and bauxite residue sand, which is a coarser type of bauxite residue produced in some refineries, and now you add some more byproducts like fly ash and blast furnace slag. You mix them all together, and at 28 days you have 3 megapascal of strength. Next slide. And we use this recipe in a pilot which is actually building a road near the O'Guinness refinery in Ireland, where we're going to use some 400 tons of bauxite residue along with all the other materials to make an actual road that's going to be tested for quite a long time to see how this works. Next slide. So then we go into transforming bauxite residue into building materials like lightweight aggregates and new binders. Next slide. So here, first technology comes from ZAC, a company in Berlin, where you can see the pilot plant they have set up there, where they take bauxite residue plus some fluxes and a special type of processing involving some thermal treatment, and transform bauxite residue into these little small spheres. They call them smart spheres. Basically, it's lightweight technical sand, which can be used as lightweight aggregates according to standards, European standards. Next slide. In Leuven, in KU Leuven, another technology has been developed where they take bauxite residue, mix it with fluxes, and do a heat process to vitrify the bauxite residue and then mill it in order to create a precursor for different types of binder systems. So you can use that in a hybrid cement if you mix it with OPC and water. You can use it in a sort of a geopolymeric cement or even in geopolymers. Next slide. And this technology has already been piloted. Here you can see some pictures from Leuven and from Technical University in Aachen, where they did the smelting and produced this small black beads that you see there, which is the vitrified BR. They had produced some 5 tons of that. Next slide, please. So yeah, here are the results of the test done in this technology. Next slide, please. And there are some publications there at the below. Then the next major task, work package, if you want, in our project was to extract iron from the bauxite residue. Bauxite residue is 40 to 50% iron oxide. So next slide. Elkem in Norway did a pilot test in extracting the iron in an electric arc furnace in order to produce ferrosilicon and slag. They tested more than 8 tons of bauxite residue, producing some 700 kilograms of pig iron and 2,000 kilograms of slag. And they got a pig iron that has 3.3% silicon inside, so it's a good raw material for them to produce then ferrosilicon alloys, and in fact it's within specs and could be used commercially. Next slide. Also at Mytilineos, we tried a different recipe, again with EF smelting, this time in a big, slightly bigger furnace, where our goal was to extract pig iron and at the same time fix the slag in a very specific chemical system, to form calcium aluminate slag. So we did some tests and achieved the mineralogy we wanted. Next slide. And I will come back to the slag in a few slides from now. So next slide. Yep. So microwave furnace technology. Next slide. That's a different type of furnace. To a prototype furnace has been developed. Here you can see microwave radiation used to roast the bauxite residue and create a mixture that you can separate iron with magnetic separation afterwards. So next slide. And this rotary kiln microwave furnace, the first of its kind, it's been built into a pilot, and it's going to be finalized within the end of this year and tested in industrial operation. The pilot's going to have a 30 kilowatt microwave power capacity. Next slide. And finally, we go to hydrometallurgy, where we try to extract rare earths and other elements. Next slide. From the slag. Here you see the slag I mentioned before. We made the calcium aluminate slag, and now we have leached it. We have created a solution that has alumina and soda, which is things that we want back into our alumina plant, and then a gray mud, which is a calcium carbonate byproduct. Next slide. Next slide, sorry. From the calcium aluminate gray mud, we can recover rare earths, or we can go directly to the extraction of rare earths from the slag, where you see here results from Aachen, where they have achieved 90% of extraction in various in aluminium, titanium, and rare earths. Next slide. Also, there is a pilot ongoing for gallium extraction from liquor. That's another critical raw material. And here you can see the solvent extraction pilot. Next slide. And here you can see the results where 100 liters of the Bayer solution have been tested and successfully recovered more than 97% of gallium found inside and isolated this gallium from the Bayer liquor. Next slide. Finally, we're putting together a house, next slide, to demo to show how these building materials can be used together. One idea is to use bauxite residue slags in cement. Jack. Next slide. No. Yeah. Next slide, sorry. Keep moving. Yeah, and here you can see various building materials produced at resourceful and geoline using bauxite residue in applications and bauxite residue slags in various applications like bricks, tiles, tables, and so on. Next slide. And all this together will come into a demo house. You see the location that's near the Tilneos alumina plant. Next slide. Where it's going to be a sort of house built for conferences and exhibition of these types of technologies. Next slide. So here you can see the materials already in production in Belgium, in Resourceful. Next slide. And we come to the end. So we have all these different pilots. We have 3 alumina producers inside the project. What we want to do now is make the feasibility studies from the results of all these technologies and combine them together in a solution that makes sense for its plant. Next slide. And for its location. The initial pre-feasibility study has been done, and we're currently connecting the dots, as you see in this slide. Next slide. It's very important, of course, in this type of project, other problems. Hopefully, we will be able to give a good answer by the end of this project and move forward to policy recommendations and communication to stakeholders to be able to launch the technology. Next slide. Yeah. And to that effect, also the project is doing some work, especially for framework and policy. Next slide. But the main idea is to identify regulatory barriers and opportunities and suggest, where possible, recommendations towards the industry and the European Commission. Next slide.
Thank you very much.
Yeah, and here you can see some of our main outcomes so far, which includes several policy briefs and so on. So I think the last slide, is just the consortium, which has some 20 partners working on this for the last 3.5 years. So thank you very much.
Thank you very much, Efthymios. Thank you very much, Efthymios, for this fantastic presentation about the project removal. We don't have questions on Slido, therefore we are now leaving for a short break and we'll reconvene at 3:30. Enjoy the break. Welcome back to the second part of these presentations on success stories of secondary raw materials, improving resource efficiency and circularity. I hope that you enjoyed the coffee break. We are now moving to our fifth success story, that is the project Collectors. Collectors focused on identifying good practices for municipal waste collection that would lead to high-quality recycling. This success story will be presented by the coordinator, Tjerk Vardenaar. Tjerk works as a managing consultant for EGEN, a European green innovation and funding consultancy firm. Tjerk is a specialist in the field of circular economy, waste management and recycling. He has coordinated projects on economic assessment of waste management strategies, on circular economy funding, and developed strategic roadmaps for circular economy implementation. The floor is yours, Tjerk.
Thanks, Susanna, for this kind introduction. Yeah, indeed, my name is Tjerk Vardenaar, and for the last 3 years, I was allowed to coordinate this project. I think it's good to start with briefly explaining that Collectors is a CSA project. That means that our project was not a research project or a demonstration project, but we focused on what is called coordination and support. And that means that we did not do a lot of fundamental research, but that we tried to identify what kind of information and knowledge is already available and made that better available throughout the research and waste management community. Because we started with the observation that, of course, waste collection is a crucial element and a crucial step in recovery of secondary raw materials. And also that a lot of cities and regions were actually able to do that in quite a good way. However, all this information and best practices were quite dispersed over different countries in different languages or focusing on specific elements of the waste management system. So what we did as a starting point, we tried to bring the available information together and harmonize that. And then in a second step, try to get a better insight into what the overall performance was of different waste collection systems. And based on that, support decision makers in shifting to better performing systems via capacity building and establishment of implementation guidelines. Next step. Yes. So we followed for that 3 main phases in the project. Started first with an identification phase. As said, there are already quite a lot of municipalities, regions that have quite good performing waste collection systems. So we started with a mapping, identifying these different studies. We managed to get more than 250 systems in our inventory. In the second step, we looked into more detail into 12 specific case studies where we assessed these different systems from a very integrated perspective. So looking on economic, environmental, as well as broad performance aspects. And finally, translate this in information for decision makers to actually be able to either implement better waste collection systems or set the framework, the European framework, in such a way that it actually motivating and incentivizing local and regional decision makers to make the transition towards better performing waste collection systems. Well, in this presentation, I don't have time to go into really depth into all the results, so I will highlight 2 aspects. That is first on the next slide. Our web-based platform of waste collection systems. So this is a picture on how that looks like. As I said, we identified around 250 different systems throughout Europe, and we put them in our web platform, allowing decision makers to look for similar cities and see and identify what kind of systems are in place there. So we categorize the systems based on characteristics of the region, as well as characteristics of the waste fraction. Then on the map, different systems became available. And then on the next slide, regional and local decision makers get information on how in a different system waste collection system was actually implemented, who are the stakeholders involved, what more or less the costs are, as well as the performance, as you see here on the slide, for example, the collected quantities for different waste fractions, as well as capture rates. Then the other aspect that I would like to highlight in my presentation here is on the next slide, is that we spent quite a lot of time in translating what we identified into both into policy support. On the one hand, guidelines for successful implementation, and these guidelines are focusing on the local and regional level, where we tried, based on the results, provide them a combination of technical, organizational, and financial guidelines. And what we specified in this aspect is that local, regional decision makers always have to make decisions in from a multi-criteria perspective. So we try to highlight what is the trade-off between different aspects and how within your local context you can make decisions, either more focusing on economic or financial aspect, for example. The guidelines provide information for local and regional decision makers, both in generic, so how do you set up your generic waste collection system, as well as some elements focusing specifically on a waste fraction, where we focus on paper packaging waste, electronic waste, and construction and demolition waste. And then the final aspects are framework recommendations. These are recommendations for the European level, focusing on what kind of improvements can be made for the Waste Framework Directive in order to actually ensure that at a local level, local and regional decision makers are able to make this transition. And also here we made a division between more general guidelines. So you can think about how can you actually come to a more harmonization and clarification on separation guidelines. So making sure that in different member states, we all use the same types of bins, the same types of signals, etc. How can you actually set proper financial incentives to stimulate better sorting at local and regional level? But also what is important, and that we try to contribute to mostly in the Collectors Project, of course, is how do you improve knowledge and information sharing between different systems. So this is more on a general level, but we also focus on aspects to actually improve waste collection on specific fractions. So you can think, for example, for how can you actually improve the EPR system and improving EPR fees based, for example, on repairability or durability of different fees, and make sure that there is a fee modulation in place. Or for construction and demolition waste, how can you actually set the system in such a way that you get an effective market for secondary construction demolition waste. Next slide. So thank you. This was a brief introduction of the Collectors Project. Happy to take your questions.
Thank you very much, Tjerk, for this fantastic presentation, brief but fantastic presentation of the project collectors. We don't have by now any questions on Slido, and therefore I would like to introduce the next presenter, Shahrzad Monosheri. She's the project manager at the World Resources Forum and will present us the sixth and the last success story of this afternoon of the project Sea Waste. And Sea Waste developed a voluntary certification scheme for the collection, transport and treatment facilities of waste from electrical and electronic equipment, as well as batteries. Shahrzad works in the area of sustainable management and responsible sourcing of primary and secondary raw materials, and she has coordinated and contributed to several international projects funded by the European Commission, and she is engaged in development cooperation projects led by the World Resources Forum. The floor is yours, Shahrzad.
Thank you, Susanna, for the introduction. Yeah, thanks a lot for the introduction, and thanks to all organizers for inviting the Sea Waste project to this session. Next slide, please. Yeah, as Susanna mentioned, the project voluntary certification scheme for waste treatment or sea waste was created in 2018 with the main objective to develop and validate a certification scheme for collection, transport, and treatment facilities of key types of waste containing reasonable amounts of valuable and critical raw materials. The project was coordinated by World Resources Forum and implemented by a strong and multidisciplinary consortium that brought expertise in waste collection and treatment, critical raw materials, research, as well as the standardization and certification process. Sea Waste was a 2.5 years coordination and support action like the collectors project, and it was finalized in April 2021. Next slide, please. Thanks to previous presentations, maybe I can keep this slide a bit shorter. The project was obviously a response to the challenges associated with sustainable access to critical raw materials that are essential for high-tech industry and emerging technologies. And as we know and already heard today from previous presentations, the supply of these materials is associated with environmental, social, and governance risks. Obviously, access to secondary sources of critical raw materials is one of the measures to mitigate the supply risk, but the current challenges related to recycling is that for many critical raw materials, especially the ones needed for high-tech applications, secondary production through recycling makes only a marginal contribution to meet EU demand of critical raw materials. And the other challenge is that recycling of critical raw materials is a complex process, and to increase recycling rates, various but interlinked solutions need to be considered. And in order to implement these solutions, policy actions, regulations, and an improved legislative framework is needed. Among different approaches and solutions, the standardization activities are needed to support these policy actions, which can also lead to level playing field in this area. And this was basically why the Sea Waste project was born. Next slide, please. Next slide, please. I think we missed one slide, but it's okay. Okay, yes, the approach, sorry. Yeah, to achieve the overall objective of the project was followed it in 5 key steps. First, understanding the situation by mapping the existing recovery practices, standards, and verification schemes related to valuable and critical raw materials, basically to understand what is the situation. Then develop new requirements and the related certification scheme and verification process. And we also wanted to test and validate the requirements and check their functionality. Based on what we learned, then we developed a roadmap for long-term sustainability of the scheme, and we provided recommendations for increasing recovery of critical raw materials. And the last but not the least, the step was that we wanted to ensure a transparent stakeholder participation through conducting various consultation process. With this short introduction about the objective and the approach of the project, I would now zoom into the key results in the next slides. Based on a set of economic and technical criteria that were defined at the beginning of the project, we first defined the key critical raw materials equipment, key critical raw materials components, and the type of target CRMs in each group. And as shown in this table, our focus was on waste electrical and electronic equipment and batteries in waste electrical and electronic equipment, or V, and end-of-life vehicles, ELVs. And the key components that we considered in our scope were printed circuit boards, lithium-ion batteries, lead-acid batteries, fluorescent powders, and neodymium magnets. And I should mention that in our scope, in addition to the critical raw materials, we included the valuable or precious metals that when I talk about the critical raw materials in the next slides, these are also included. Next slide, please. One of the cornerstones of the project was that we didn't want to develop a new standard from scratch or reinvent the wheel, basically, but we wanted to take stock of what is already available and build on what is functioning in the standardization world about the recycling of, in general, in general in metals or critical raw materials. And we wanted to focus on the gaps. To do this, we mapped more than 60 relevant normative frameworks, and the results show that there are very few CRM-specific non-technical requirements, very few technical requirements with relevance for key CRM components, and hardly any technical requirements specifically for critical raw materials recycling. Another key result of this mapping exercise was that the EN 5625 standard series, which is the European standard on collection, logistics, and treatment requirements for V adopted by Senelec, can be considered as a basis for development of the C-waste requirements. And in cases where Senelec was not sufficient, then we took stock of the other existing standards at international level, like ISO documents or UN guidelines, such as the Basel Convention. Next slide, please. This being said, we then developed new set of normative requirements, including technical requirements for the key CRM components that we identified, as well as traceability requirements and sustainability requirements, and covering the whole value chain from collection, logistics, and transportation, pre-treatment, and final treatment facilities in the value chain. Next slide, please. And to ensure the conformity of the facilities with the C-waste requirements that we have developed, then we also developed the related assurance system, verification procedures, and manuals that include manuals for the operators and the auditors that could be used for auditing processes. Next slide, please. And once the requirements and the assurance system and the verification procedures were defined, the feasibility and practicality of these were tested in real-life operations through pilot audits. Between March and December last year, 2020, we conducted 20 pilot audits in Belgium, Colombia, Italy, Portugal, Rwanda, Spain, and Switzerland and Turkey, covering again the entire value chain. And through these pilot audits, as well as several rounds of consultation process with a wider group of stakeholders, we collected more than 600 comments, and we analyzed the kind of readiness level of the operators for recycling of critical raw materials. Next slide, please. Based on all these learnings, we then identified a set of integrated policy options for improving the recovery rates of critical raw materials. The first pillar of this recommendation was, of course, on legislation. We recommended that there should be legal obligations to recover critical raw materials, and there should be mandatory recycled content for this group of materials, and maybe something in the direction of the proposed battery regulation, which seems to be a promising action. These are needed to create a market pool for recycling of critical raw materials, and of course, legal obligation without existence of economic viability will not work. The second pillar is to make sure the implementation is possible. Basically, in this pillar of the recommendation that we had, we defined that there should be markets for recycled critical raw materials, and there is a need to invest on technologies and infrastructure for critical raw materials recycling, and new collection models or grouping of critical raw materials rich products is needed. And of course, the next important pillar is on monitoring and reporting. And here we also recommended to use the opportunity to tap into new models like digital product passport, which can enable better traceability and knowledge about the location or concentration of CRMs in products. And obviously, legislation will not work if there is not enforcement, which is the next pillar in our set of recommendations. Next slide, please. And the last but not the least result of the project was a roadmap for the rollout and long-term sustainability of the scheme. Basically, we developed the scheme, we developed different components, documents that are related for this certification scheme, but we also wanted to make sure that it will continue living after the project. So with this roadmap, we defined very concrete steps. The first step that is considered in this roadmap is that to make the Senelec standard mandatory and to ensure effective impact on critical raw material recovery. This would require, of course, revision of the Senelec 5625 standard series and updating best available technologies to include aspects related to resource efficiency. The next step in this roadmap is to obviously we develop the C-waste requirements based on the Senelec standard, and now the next step is to incorporate the C-waste normative requirements into the Senelec series. Then the next step is to call to action for member states for improving the collection of critical raw materials rich fractions, together with concentrating CRM-rich fractions at collection stage, and also conducting awareness raising campaigns that is very crucial in this for this action. And this is expected to increase the input needed for end processing. Also, creating market pool by promoting the use of secondary critical raw materials through regulations requiring a minimum amount of recycled content in products. Facilitate demand for critical raw materials by creating a trading platform for recycled components or materials, therefore also facilitating the trade process for companies that are recovering critical raw materials. materials, stimulate economic viability for recovery by means of policies and measures that are aimed by would lead to optimizing the economic viability of CRM recovery processes, including dedicated incentives schemes for recyclers or for producers that are using secondary critical raw materials. And the last step in this roadmap is to stimulate and invest in research, development, and technology for better and more efficient processes for recycling critical raw materials. And with implementing these steps, it is expected to encourage the investments needed to make recycling critical raw materials more commercially viable in Europe and help us become less reliant on existing sources. Next slide, please, which is my last slide. With this, I would like to thank you again and give the floor back to you, Susanna.
Thank you very much, Shahrzad, for this very interesting presentation about the project Sea Waste, aiming at developing a voluntary certification scheme. Very useful and very interesting indeed. There is one question on Slido for Tjerk, and the question is, how have you promoted your project results to policymakers to ensure they are actually used? Have you measured engagement with the produced content? Tjerk, the floor is yours to answer this question.
Yeah, thanks, Susanna, and thanks for this relevant question. I think how we approach this is twofold. I think very early in the project and maybe already in the application phase, we try to involve users as much as possible. So when I showed earlier, like the web-based platform and the criteria that are there and the description that are there, it's not that it was the consortium that decided that these are the most relevant parameters. We selected these parameters in dialogue with local regional stakeholders and asked them, when you have to make a decision on how and when you implement a waste collection system, on what parameters do you do that? And based on that, we decided then on how to harmonize the data that we had. So we involved them early on and made sure that what we developed was actually in line with the needs and in line with how local and regional decision makers make their decisions. Second thing is then when the products were there, how do you make sure that it is actually being used? And of course, you only have a limited influence on that. But how we did that was to make sure that within the consortium, there were the right partners, meaning the associations representing local regional authorities as well as EPR schemes, to have them on board and helping using their working groups to actually test and experiment with the results that we had. And then for the more broader guidelines on the Waste Framework Directive, what we did there is trying to get proactively in dialogue with colleagues of Susanna at DG Environment and see how what we find could align with the attempts that were being made there on harmonization of waste collection systems, for example. So I hope this answers.
Yes, that's true that the results of this project attracts the attention of several people involved in preparation of the legislation on waste, including our colleagues from DG Env. We don't have more questions, and let's check the last. Okay, so we have one last question for Thomas. Thomas from the project Nemo. And the question is, what about arsenic in the tailings?
Yeah, hello, good afternoon. With respect to, let's say, heavy metals in general, we're running leaching tests. So let's say all the concrete we make is also being tested into second and even third life. Let's say the tests are running on the pilot concrete, and at the moment is ongoing. Let's say based on the raw composition of the tailing, I don't expect big problems with arsenic or other heavy metals, but let's say by the end of the project, we for sure have all the, let's say, reports in terms of heavy metal leaching.
Thank you very much, Thomas. Now it's time to thank to the 9 presenters that we had this afternoon, who showed us 6 success stories on secondary raw materials, improving resource efficiency and circularity. And it is now time to give the floor to the moderator, my colleague Yolanda, for the panel discussion. From my side, it has been a pleasure to be here, and I wish you a very nice rest of the day. Thank you very much for your participation. Yolanda, the floor is yours.
Thank you, Susanna. Yeah, indeed. Thank you. Thanks to all the speakers for the presentations and for contributing to this excellent session. And now it's time to open the panel discussion on secondary raw materials, collection and recovery schemes. Well, as you know, resource efficiency and recycling constitute one of the pillars of the EU raw materials initiative and the EU raw materials strategy. So this is not just a marginal question. It is quite central and important to realize the European Green Deal and the twin transition that we are aiming for. And would like to maybe start by discussing some issues related to the potential industrial impact or industrial application of some of the innovations that we have seen nicely presented this afternoon. Maybe I would start asking Laura from Platinus. Well, Platinus is research and innovation action. This is a bit lower in, still a bit lower in TRL than removal or Nemo or Secrets, the other innovation projects that we have seen this afternoon. But probably now that the project is finished, you would be already able to give an indication. Do you think that Platinus has the potential to replace the existing recovery methods for platinum group metals? And if so, what would be needed? What would be crucial to be further developed or improved? And which do you think will be the challenges to succeed in that?
Okay. Hello. Good afternoon. Thank you, Yolanda, for the question. Yes, well, regarding your first question, well, the Platinus project, we have demonstrated that we can obtain PGM metals that can be used to produce new catalysts with same or even better performance than the commercial ones. No, that is on the one side, and also we have demonstrated the economic feasibility. As the project, according to the LCC cost, it has a payback of 6 years. And also, according to these calculations, also it seems that the Platinus process, I mean, the PGM production with the Platinus process could be perhaps cheaper than the production of PGMs using primary sources. No? So, well, as a starting point, we think that is very promising. But yes, of course, we need to optimize some aspects. I would say that the most critical one would be probably the reduction of steps, especially in the separation part. We still have a lot of steps, and reduction the steps and the chemicals used in that part will be desirable, no? And regarding the challenges to implement it, it is always hard to replace processes that are already working in the market. And for that, we need to have a really competitive process. No? So I would say that, yeah, in line with I said before, is what the research beyond Platinus should be doing, no? Optimizing the reduction of steps and so on. And we do that in the PICO project, actually. We are continuing that now in the PICO project.
Okay. Yeah. Because the PICO project is actually an innovation action, so the next step, the step following research and innovation action. Well, I think that this is in general a major challenge for any technological development. You have research activities with maybe great results, but the challenge is to survive that period of translational research, or what is called sometimes the valley of death of research and innovation, which is to move forward from that research and really manage to demonstrate at a significant scale what's your main findings from the research phase, as to make sure that you can enter the market. In fact, the innovative pilot actions were one of the targets of the EIP and raw materials, the EIP strategic plan, and secrets removal and Nemo were indeed innovation actions directly addressing these, or at least in part at this respect. Tim, is do you think that successful Horizon 2020 projects, innovation actions can be ripe for commercial rollout, or even the innovation actions that are successful and then have a lot of good results need something else to reach the market, and if so, what would be a follow-up mechanism, or do you have other suggestions, ideas? What are your views on this?
Thank you for the question. I think there is a problem inherent to when we're discussing raw materials and extractive metallurgy. It's the scale. To reach TRL 8, when you're discussing, I don't know, iron production, I don't want to even go into critical raw materials. You need large scales. Industries of raw materials are very big. So pilot scales, when we're discussing a hydrometallurgical process, would mean a continuous pilot. Now, it's very difficult to design and operate a continuous pilot at sufficient scale for hydrometallurgy, for example, within the framework of a Horizon project. The size requires an investment that's beyond usually the scope of the funding and the timeline, probably. So we say that we are close to TRL 7, 8, but I think in many cases, and if you go to pyrometallurgy, it's even more so, right? If you think of the sizes of the industrial furnaces that are being used today. So it's very difficult. While we do get at a very good TRL level for research standards, if you want. If we want to discuss industry, we are close to the proof of concept, right? So there is a next step there where you would need to go to a bigger pilot. Now, I don't know how this can, to an industrial pilot, if you want. Industrial pilot is not necessarily the one run within the industry. It is a pilot that from which the data are directly used for designing your future factory. So that's not an easy task to do. Therefore, this is what is missing, I think, in my experience. When you get to the point you proved the idea, you did a large scale campaign, you did a lot of tests, and now you have enough data. You basically have enough data to do a good capex estimate and a good opex estimate plus minus 30% or something. And if you can do an initial scale up study and go to the board of a company and say, okay, guys, this is where we headed. The next step would be to do an additional project. I don't know if this is a public funded project or if this is a private project or this is something for ERMA or some other type of instrument.
I would say that maybe I don't know if this can apply to all the cases because each project and each case might be a world, but some part of this could be covered by the program of the EIT and raw materials.
Yeah,
we do have a few examples of projects that after Horizon 2020 were followed up in the EIT raw materials. But as I say, it might depend on the project and the topic and the status that has been reached in Horizon.
Yeah, that's absolutely true. And I happen to, I will be starting one of those projects because in the scale project, which finished last year or so, which was on scandium extraction, and we did have an industrial pilot. We got very good results. And now we have been granted a chance through EIT to run 3 consecutive years of pilot testing just to optimize this flow sheet. And it's, I mean, if you look at the ambition in that project, you would probably say there's not a lot of ambition because what we're doing is simply running again the pilot for 3 years and optimizing things here and there, recycling a raffinate, increasing a bit the efficiency there and so on, in order to be in a position at the end of the project to say, yeah, now we have enough data to consider an investment and so on. So, yeah, I have been fortunate enough to see this happen in the EIT raw materials. But this is a case where indeed the size of the processing allows it, right? If we were discussing, I don't know, some hydrogen-based iron production, that would not be the case.
Yes. Okay. Thank you. It's an interesting reflection. I would like now to go to Thomas on the Nemo project. The Nemo project is targeting a very specific industry for end-use application. You aim to use or to upcycle the materials you are recovering from the tailings for their application in concrete. What is the role of the concrete industry in the European raw material sector towards closing the loop? What are your views on this?
Yeah, thank you, Yolanda, for the question. So what I believe, I think I can follow Eftimis his reasoning. Scale is also here. Extremely important if you think of the size of these streams, like in Nemo, as Arne projected, it's like 600 million ton annually produced. You need to find an industry that can deal with such kind of, let's say, such an amount of residues and secondary materials. And I think then only concrete is, or let's say construction materials, is even maybe an order of magnitude bigger. If you think of cement production, which is like 4 billion tons, and the amount of sand and stones that is taken, it's even a factor 5 or 6 times higher. So I think in order to be able to close loops of such enormous industries, you need an industry that can capture such an amount of material, and then the construction material is, I think, the one that can take it. Of course, not everything has to be, let's say, put into concrete. There should be some, let's say, reasoning and maybe also rethinking of the secondary raw materials. I think blast furnace slag is a perfect example of the last decades where it was considered a waste, and I think now people or steel factories even engineer the slag to be, let's say, wanted by the cement industry. So if, let's say, a lot of these secondary raw materials can go through the same evolution, I think that would be a great step, and also the construction industry would benefit from it to be more green and more circular. Okay.
Indeed, it's an ambitious vision. Interesting. Let's move now a bit from perspective industrial deployment to the potential environmental gains linked to valorization of waste and recycling. Pauline, the focus of your work on secrets has been on LCA and on the potential environmental gains. Indeed, I think that you have mentioned it at the end of your presentation, but if you could briefly remind us again what was the major challenge that you have been facing to complete your work. What's the challenge when looking at the environmental impact and gains in these raw materials projects?
Yes, of course. So, like we have seen in the results, we see that this secondary source of raw material is actually quite beneficial in terms of environmental impact or environmental gains. The real question when we look at results like that is always how can you compare it to a baseline, right? Because results by themselves, they don't really mean anything. So that's why we have a baseline that we're comparing our results against. And in our system, like I mentioned, we had access to primary data. Our main challenge is to be able to actually understand and measure and get robust results on what is happening in the current practices, mainly in China. We don't have access to primary data. It's more complicated to reach out to the different sources that we find online. I even found a paper recently published in October this year that is reviewing all the literature out there about rare earth elements extraction. The LCA of rare earth elements production. And the conclusion is that there is no good enough, and we never have good enough data, but there's no data out there really allowing us to say for sure that the environmental impact of the rare earth extraction in China is this or that. So it's still really an ongoing process. And actually, I'm quite optimistic still. Like we see a lot of momentum, like today with the conference we have today, but with other events that were happening or will happen. We see a lot of momentum, a lot of interest. There are associations that are getting created around these rare earth elements and these critical raw materials. And I think people start to understand that it's crucial for us to get the data. So I'm optimistic about this. I think we see more and more, really elements and data getting published and getting verified. So I think this is really positive.
Okay, thank you. Now, a last question to be answered very briefly, because we are running out of time, by Cherk and by Sherazad. What needs to be changed in waste management and in general? For the case of collectors, and maybe more specific for the recovery of CRMs related to the work of sea waste, so that we can indeed improve the recovery.
Yeah, thanks. Of course, a difficult question to answer very briefly, but let me make an attempt. Because if you talk about what has to be changed on the current waste collection process, I think there can be changes along the full value chain, from product design to consumer behavior. However, pinpointing one thing, I think it's very important that we start to have a different perspective on how to organize waste collection, because waste collection has always been a demand-driven process, where it is seen as a service for us as consumers, something that is being done by the city or by a regional authority, anticipating on bringing in an efficient as possible way your waste away and making sure that it is no rubble anymore in the street. However, when you talk about waste collection in a circular economy perspective, and when you talk about it from the idea of recovering secondary raw materials, waste collection becomes also an explorating view. And I think what's important there is that in addition to providing a service to consumers, you are also sourcing the materials for a new cycle. And with that in perspective, in waste collection, you need to adopt also a perspective from a market-driven perspective. Mm-hmm. And I think this is very important, where you should look at waste collection, maybe not only focusing on having as much quantities as possible, but look at it on what are the qualities that you actually can recover, both in a technical way as well as an economic way. And this is a total different perspective. I think if you want one change, I think this is the change that you're looking for.
And very briefly, Sherazad, on critical raw material particularly?
Yes, thank you, Yolanda, for the question. Maybe I will focus on the gaps that we identified when we were talking to the recyclers, to the operators, that gave us insight into what should be done basically by introducing these gaps and obstacles that they have. I can say that, as I said, we received many comments, but maybe if I want to highlight the most important ones, the key point was that CRM recycling is currently not economically viable. And this is due to the high investment costs that is needed for installing the recycling technologies. Or the other reason for that was the low and volatile prices of critical raw materials, or lack of market for secondary metals. And the other point, maybe I will just very quickly summarize.
Yeah, just mention, yes.
Exactly. Lack of recycling technologies was another point for some of them. Difficulty to access components, again, due to the design of products, as Jack was mentioning. Also low concentration of CRMs in products, which means more waste is needed to recover critical raw materials. And of course, lack of legal frameworks was another issue that will lead to a level playing field, and without that, it will not work.
Okay, thank you. Sorry to have to hurry the timing, but we are reaching the end of the discussion and of the event almost. But to conclude this event, I would like to give the floor to Jonas Hedberg, acting head of sector of the raw material sector at HDA, who will provide some closing remarks. Jonas, please.
Thank you very much, Yolanda. So I just have a few minutes, and it's very difficult to close such an event with such a vast amount of material and outcomes having been presented. But what I would like to start with saying is that what we have seen now in this event, we have seen the different projects and how they're working on two fronts to address the raw material challenges. They work on decoupling of the need for primary resources, so particularly the critical raw materials, from the increased demand that we see from this green and digital twin transition, or that we expect from this transition. All this while covering the need that remains from state-of-the-art sustainable mining and processing. So of course, part of this story is, as we have seen, is the exploration for new resources in Europe. So we need to accelerate that exploration, and that's all this while addressing the valid concerns that come from EU citizens that unfortunately is also rooted in real events. So they have to be taken seriously. And I think it's what you have seen here is it's impressive to see how our exploration projects have went beyond the expectations that we had in our Horizon work program, and really been working very thoroughly on this issue of public acceptance and social license to operate. And we see that all these exploration projects have done a fantastic outreach work, and also researched a lot on this public acceptance. I heard just an example here. I heard Sandra Lorenz mention the fact of gaining trust, and also the fact that it will take time. And I think that is really a key thing here when you work with public acceptance. It's not going to go overnight. So we heard about examples from Pacific, this beautiful passive non-invasive seismic methods, which is developed in EU-Canada collaboration. So we're very happy to see the international collaboration being taken seriously, which is really crucial for raw material issues. We saw examples of smart explorations, focus on young professionals and a very market-oriented approach. So that led to a very big amount of publications and prototypes coming out of that project. Very impressive. In fact, also taking the courageous action to try to factoring in the term social license to operate, or public acceptance if you want, in this exploration decision process. And then we came to the mining part, right? We need mining techniques that work for Europe. So that goes in hand in hand with the greening of our economy. And we saw in this sense the examples from X-Mine and Impact, which was looking at increasing the autonomy in value chains through this small-scale, selective and flexible mining of critical materials that can be quickly deployed on site, and that could work in a very densely populated Europe. So it was also nice to see how they did this connection to the local communities, which we need. On the other hand, X-Mine, which used the real-time online sensoring, and they were kind of integrating the questions of exploration and mining, so that they really get a much better economic and environmental performance out of that. Then finally, we had the part that was working with the recovery of these critical elements in byproducts, which needs to accelerate. We saw the example of Secretes and Platinus, who created some innovative low environmental impact European supply chains of these metals that are needed for the green technologies. Secrets, on their hand, they looked at using rare earths coming from the fertilizer production, which really led to lower environmental impact, as we saw. And then Platinus working on recovering these platinum group metals from catalysts. On the other side of recovery, we also had the removal of Nemo, who they were very impressive. You could see how they worked of this great problem of mining waste. So both in terms of bauxite residues, red mud, and sulfidic mining waste. And by doing this, they are really turning environmental problems actually into the buildings that we live in. So, but also getting other valuable metals out of it. So that's also very impressive to see. And then finally, the much needed work of collectors and sea waste on the framework conditions related to recovery of waste. So just let's remember that what we have seen today are only some small examples or highlights from everything that comes out of Horizon 2020. One way that you can see more of this is by looking at the innovation radar site. it's possible to see some of the innovation highlighted that comes out of our program, Horizon 2020. And some of the final things I would just like to say to close this off is that we can see that we are kind of on a path of increased attention to these issues related to supply of raw material. Now we're talking about the green transition, but it started already in 2008, at least in terms of EU policy. It probably started before, but in 2008 with the Raw Material Initiative, and then the EIP, the stakeholder community, built the Horizon 2020 work program, and this really became an important instrument to achieve these necessary developments for sustainable raw material supply. So in this, there was a dedicated chapter to raw materials in Horizon 2020, and now in Horizon Europe, we still have a lot of focus on raw materials, and now it is split between two different destinations, so climate neutral, circular and digitized production, and the increased autonomy in key strategic value chains. So that kind of reflects on its importance for this transition that Europe is going through. So we already have launched 4 major goals, covering twin transition, resource efficiency and resilience. And apart from that, let's also not forget that EIT raw materials, as was mentioned several times, and we saw the break promotions, this is a part of the Horizon program as well. So that could be helpful in terms of bringing results to the market, of course, as Yolanda and Eftimios Balomenos gave examples of. And also we have the Eramin networks, which are still launching calls in the Horizon 2020 program, actually. But as we look forward to these new calls, and what do we produce, let's not forget that the importance of the FP7 legacy, and also the importance of what Horizon 2020 is producing as we speak. So in a way, all the Horizon 2020 calls are over, but now is probably the peak of the impact that will be coming out from Horizon 2020, or the peak of the results, I would say rather, because then we have several years before the results actually enter into the market. It was mentioned sometimes in the discussion that the mining industry is a slow industry, so it might even be even slower in mining, for example, to actually get these outcomes of the research program being put into practice. Then I would just like to conclude by saying that it was great having us with you. I would like to thank you, all the participants. I would like to thank our projects, so Horizon 2020 project, and the moderators for making this such an interesting event. And I would hope to see many of you in the brokerage event that happens tomorrow, where you can get a chance to look at the opportunities in Horizon Europe. So I especially wish the technology developers and the innovators among us success in your future participation in the Horizon Europe program to help Europe tackle the challenges that are ahead. So with that said, I just wish you good continued participation in this Raw Material Week.
Thank you, colleagues. Bye.